Hello everyone, and welcome back to Math 110 Introduction to Number Theory. And in this lecture video, we're going to talk about some number-theoretic functions. So recall that for most of the course, we've been talking about the divisibility relation for the natural numbers. And in one lecture, we talked about how these define a partially ordered set, or a poset for short. And we also visualize these using Hasse diagrams. So for example, looking inside the natural numbers at all those divisors of 18, we have, for example, 6 divides 18, 2 divides 6, and also transitively 2 divides 18, because we don't show lines that are just implied by transitivity. So today we're going to talk about some functions that measure properties of this poset, and in particular, the subposet of all the divisors of a particular number. One thing is that we want to exclude 0 for most of this because most of these functions are not defined at 0. So n plus will represent the positive natural numbers. So 1, 2, 3, and so on. Natural number is greater than 0. So here are two of our functions that we're going to look at. The first is the function that gives the number of non-negative divisors of a positive natural number. So one way we could define it is d of n is the sum over all divisors of n of 1. And one sort of confusing thing that I hope won't be too ambiguous is that this d here is not the same as this d here. It's just sort of convention to write d divides n. So I could have also written, for example, the sum over all c divides n. Anyway, so if we just sum up 1 for every d in n, then I guess another way we could write this is it's the cardinality of the set of all, let's say, k in the natural numbers, such that k divides n. So that's another way we could write it. And also, by the way, this notation, sum d divides n, specifically means a sum over all d that are in the natural numbers where d divides it. This is just some special sigma notation for this particular this particular domain. Okay, so that's the d function. Another function is sigma. And this is a lowercase sigma if you're not familiar, where this is uppercase sigma. So this function, also on the positive naturals with natural values, it gives the sum of the non-negative divisors. So instead of summing up 1, we sum up d. That's another function, and it's a sort of interesting one too. So in general, we can generalize these, where sigma k of n is the sum over all divisors of d to the k, because then that way d is sigma 0, and also sigma is sigma sub 1. And this generalization enjoys some similar properties to these previous functions. There are two other functions we'll look at, and the phi function is going to be important for a generalization of Fermat's little theorem in a couple lectures. And so phi, known as the Euler phi function or the totient function, is the sum of, well, it's the number of all k less than n such that k is coprime to n. So it's the number of residues mod n with a multiplicative inverse. So we could also write it in the sum notation if we wanted. Another function that seems pretty obscure when you first see the definition, but it plays an important role in something called Möbius inversion, which we'll see, is the Möbius function. Instead of being natural number valued, this one is integer valued. And the definition of it is that mu of n is 0 if any of its ords are greater than or equal to 2. Or another way that we can say it is that it's 0, I should say if it's not square free. So if n is not square free, that means that there's some a greater than or equal to 2 such that a squared divides n. So it's 0 for non-square free numbers, and if it is square free, we do -1 to the power of the number of prime factors. Or if we wanted, we could write it as the sum of the ords, because that gives you the number of prime factors, assuming all the ords are at most 1. Okay, so those are two more functions. So we've got d, sigma, phi, and mu. So let's look at some examples for what these functions actually do. We're going to use 18 as a running example. So d of 18 is the number of divisors of 18. So it's the sum over d divides 18 of 1. And in gray, I've written out all the divisors in order. And so we're doing 1 plus 1 plus 1 6 times, so it's 6. 6 divisors. Sigma of 18 is the same, but we sum up those numbers that were in gray to get 39. So that's the sum of divisors. Phi of 18, so the number of multiplicatively invertible numbers mod 18. One way to calculate it is by brute force. It's the cardinality of the set, so I wrote out all the numbers 0 through 17 and crossed off all the ones that don't have a multiplicative inverse, leaving these 6 numbers. So this one happens to be 6 too, but that's just a coincidence. These aren't always equal. Then mu of 18, well, there's a 3 squared in there, so it's 0. If it were instead like 2 times 3, so 6, mu of 6, this would be minus 1 squared, because they're 2 primes, so that would be 1, for example. Or mu of 3 is minus 1 to the 1, which is minus 1, because there's just 1 prime factor, no squares. And just for a tip for clarity, 3 to the 3, that would be 0. It doesn't have to be a square, just it has to have a square prime that divides it, then that's 0. Okay, so an interesting property that all 4 of these functions share is that they are multiplicative. A multiplicative function on the positive naturals is defined to be it's a function where for all m and n in the positive naturals, if they are coprime, then f of the product is the product of the f's. So one way that, you can like distribute f over the product. So our goal is to see that all 4 of these functions are multiplicative. So let's first explore some consequences of this definition to get a better handle of what it can do for us and why we care. So first, just to, I guess, the most basic thing, what's f of 1? So let's say we had a multiplicative function and f of 1 is 0, then it turns out the function is just 0 for all n. So let's see how we can prove that. So we're supposing that f is multiplicative and f of 1 is 0. Then suppose n is in the positive naturals. We're going to show that f of n is 0. So by multiplicativity in here, so let's look at f of n. Well, certainly that's f of n times 1. And then by multiplicativity, that's f of n times f of 1. And then, since we're assuming f of 1 is 0, we can put 0 in and get 0. So that's what we wanted to show. So these sorts of multiplicative functions aren't so interesting. What if f of 1 is not 0? Then it turns out that f of 1 is 1. And the reasoning is pretty similar. So f of 1 is f of 1 times 1, of course. And then by multiplicativity, that's f of 1 times f of 1. And since we're assuming f of 1 is non-zero, then we can cancel it from both sides to get 1 equals f of 1, which is what we wanted to show. So those are 2 basic consequences, that f of 1 is either 0 and it's always 0, or f of 1 is non-zero, and then f of 1 is 1 in that case. Okay, so here is the next fact, and I guess the slide looks rather compact, but the point is that when you have a multiplicative function, then f of n is, if we have a prime power factorization of n, then what we can do is take the f's and then apply it to each prime power. So the reason for this, without going into a formal proof, it's straightforward, because each of these prime powers is co-prime to all the other prime powers. So we can just inductively apply the multiplicativity property for each of these prime powers. But a warning, f of p to the m is not equal to f of p to the m, because the key thing with the multiplicativity property is that the numbers in the product have to be coprime, and that is why we're just being left with these prime powers. So the way the induction works to prove this, I should say in general, because it might equal, like, for example, if the function is always 0, then this happens to be true. Yeah, so induction. We're going to do it on the number of prime powers that are present in the in the prime power factorization. So, and we're going to we're considering only n is greater than or equal to 2, because those are the ones that have at least one term in the prime power factorization. So what we're inducting on, the statement is, for all n greater than or equal to 2 with a prime power factorization, then the conclusion holds. So for the base case, k equals 1. We're not starting with k equals 0 for this. We're starting with k equals 1. Then suppose that we have this n that's greater than or equal to 2. Because k is 1, then it is a prime power. And then it's trivial, because f of n, by substituting nn, we get f of p to the m. Now the inductive step. So we suppose it's true when we have numbers with a prime power factorization with k numbers, with k primes, and we'll show it's also true when the prime power factorization has k plus 1 primes. So let's suppose we have our number, and we have it with prime power factorization with k plus 1 numbers, k plus 1 prime powers. Then by GCD properties, we know that this last prime power, the GCD of it with the product of the previous prime powers is 1, because this prime is not present in the previous list. So f of n, by just using multiplicativity, using this GCD, is this product, and the first part of the product, by our hypothesis pk, can be then written as a product of f of the prime powers. And that's what we wanted to show. And so that completes the induction. And just one last thing. So we proved that, well, yep, that's it. So that's nice. Let's look at some examples that might make us believe that these functions are multiplicative. So d of 18. If it's multiplicative, then we can write it as d of 2 times d of 3 squared. D of 2 is, well, 2 because the only factors of 2 are 1 and 2. And 3 squared, the factors are 1, 3, and 3 squared. So that's 3, and 2 times 3 is 6, which is what we saw before. What about sigma? Well, if it were multiplicative, we could apply it on 2 and 2 squared and multiply. Then sigma of 2, so 1 plus 2 is 3, just adding up the factors in these lists. And sigma of 3 squared is 13. And 3 times 13 is 39, which was what we got before. And then phi, what if it were multiplicative? Then phi of 18, again, would be phi of 2 times phi of 3 squared. And phi of 2, well, how many multiplicative inverses are there mod 2? Well, only one has a multiplicative inverse, so that's a 1. And now what about 3 squared? So so this is I got the bound a little wrong because I changed my convention while preparing. Okay, so it's the set of all k less than 9 where the GCD of k and 3 to the 2 is 1, which is exactly the same as saying that 3 does not divide the number, because that number is prime, because 3 is prime. So we can just, well, it's 9 minus 3, because there are 9 numbers less than 9 that are natural numbers. And also the divisors of 3, or the things that have 3 as a divisor are 3, 6, and 0. And so that's 6 things left over. 1 times 6 is 6, just like before. So now let's study the d function, the number of divisors function. Here's a theorem, which is that d of a prime power is m plus 1, where m is the power of the prime. So to do this, we're going to have a claim, which is that the set of all d such that d divides p to the m is equal to the set of all p to the k, where 0 is less than or equal to k is less than or equal to m. And this is probably a longer proof than it needs to be, but anyway, here is a proof. Let's suppose that d is a natural number. So, by the way, to show two sets are equal, we just have to show that whenever we have a natural number, then it's an element of the first set, if and only if it's an element of the second set. So we'll show that d divides p to the m, so it's an element of the first set, if and only if there exists a k within the bounds such that d equals p to the k. So it's in the second set. So for this if in the forward direction, so we assume that d divides p to the m. Then for one observation is that for every prime q, then because we have this divisibility, the ORD q of d is less than or equal to ORD q of p to the m. So if q is not p, then ORD qd equals 0, since ORD q of p to the m is 0 if the primes are different. And also, ORD p of d is less than or equal to m, because if ORD p of p to the m is m. So what we have from this is that d is p to the ORD pd, like that is the prime power factorization of d, and so we can use that for k, that ORD. What about the reverse? So this is that there exists a k, where k is between 0 and m inclusive, and d equals p to the k. So we assume that we have those. Then certainly p to the k divides p to the m, because k is less than or equal to m. Okay, now that we have that these two sets are equal, we can say that d of p to the m is the sum over all d that divides p to the m of 1, which is the number of divisors of p to the m. And then we can replace the set that we're looking at the cardinality of into the set of all p to the k, where 0 is less than or equal to k is less than or equal to m. And since for each value of k here, each of the p to the k's are different, then we can instead count how many k's there are that make elements, and that's m plus 1, because we need to make sure to include 0, I guess. Anyway, so that's that. So the next thing is that d is a multiplicative function. So we start out by assuming that m and n are coprime positive natural numbers, and we'll show that d of m times n is d of m times d of n. So to do this, what we're going to show is that this function is a bijection, this function f that I'll define right here. And what f has as its domain is the set of all pairs of natural numbers such that d1 divides m and d2 divides n. And the codomain is the set of all divisors of the product m and n. And what the function is defined by is simply multiplying the two numbers that are in this pair of numbers. And so, yeah, the claim is that this is a bijection. And the details in here are an exercise for you, but we can show that it's both surjective and injective, which is what we need for it to be a bijection. And so for surjective, so suppose that d is the divisor of m and n. So we have an element of the codomain. Then I claim that d is equal to the product of the GCDs of d with m and d with n. So if we can write it that way, that means that, well, we can use this for d1 and that for d2. Okay, so the exercise is to show that equality. Injective is that if we had two different pairs of numbers whose products give the same thing, so two pairs from the domain, then the conclusion would be that d1 equals d1 prime and d2 equals d2 prime. So here's sort of how the d1 case goes, d1, d1 prime. So d1, one can show that d1 times d2 is GCD with m is actually d1. And also d1 prime, d2 prime's GCD with m for the same reason is d1 prime. But because these products are equal, we can link this up into a chain of equalities to see that d1 is d1 prime. And replacing m with n, we get d2 is d2 prime. Okay, so given this bijection, then, well, d of mn is the number of divisors of mn, but the cardinality of a set is equal to the cardinality of a set it's bijective to. So we can replace it like that. And then this set, we can actually write it then instead as the cardinality of the Cartesian product of d1 in n, where d1 divides m, and the other set is this with d2 and n. And then the cardinality of a Cartesian product is the product of the cardinalities, so that's what gives us that it's dm times dn. So as a corollary, we can put this all together. Because it's multiplicative, we can just calculate what it is on prime powers and then multiply all the results together. So d of n is the product of all the powers in the prime factorization plus 1. So now let's look at sigma and go through a similar sort of thing, seeing what it is on prime powers, showing it's multiplicative, and then getting a formula for prime power factorizations. So if we have a prime and an exponent, then sigma of p to the m is this expression here, which is a way to write the geometric sum 1 plus p squared through p to the m. So sigma of p to the m is the sum over all divisors of p to the m of d. And like before, instead of summing over all divisors, we can instead sum over all powers that d could have, because it has to be a prime power. So it's the sum over all p to the k. And it's a geometric sum, so there's that formula. Now let's show that it's multiplicative using actually like the same sort of argument as before, relying on that bijectivity claim. So suppose that m and n are coprime, where we calculate that sigma of mn is the sum over all divisors of mn of d. Because of that claim, we could also, instead of summing over the d, we could sum over the product of d1, d2, where d1 divides m and d2 divides n. So summing over, there's a ruling here, which is that this is also d1 divides m, sum over d2 divides n, d1, d2. But this product, so d1 and d2 don't depend on each other in any way. So we can factor it. And so this is sort of a standard manipulation of sigmas. That if you have sigma, or a multiple sum of a product of things that are independent, you can turn it into a product of the sums. Yeah, so we unfoiled it. So, and then that gives it as a product of the sigma functions. So as a corollary, if we have our prime power factorization of a number, then sigma of n is this product of, so vertically stacked on top of each other across this vinculum are the different values you get for each individual prime power. Yeah, so this is a way that we can calculate sigma. So in general, both of these functions that we just saw, d and sigma, are from the following construction. So let's say that we have a multiplicative function with the values in the integers, or really anything if you want, that has a product. Then let's define capital F to be the sum over all divisors of n of little f applied to that divisor. So the claim is that if this little f is multiplicative, then this sum over divisors function is multiplicative. So it's like really the same argument as before. Big F of Mn is the sum over all divisors of little f, which by that claim is the sum over divisors of the first number over the sum over divisors of the second number of f of the product of those divisors. And then, because f is multiplicative, we can then apply that property, because key here is that the GCD of D1 and D2 is 1, because m and n are coprime. And so we can undistribute and then get that it's big F of m times big F of n. So, for example, sigma k, that function that generalized both d and sigma, which is the sum over all divisors of d to the k, it's multiplicative. That's because the function that we're summing over, this power to the power of the k function, is multiplicative because it's just a exponentiation rule. So when k is 0, it's sort of trivially multiplicative because 1 is 1 times 1. Now that we've seen the d and sigma functions and their multiplicativity, I thought it would be nice to look at Möbius inversion and see what the role of this mu function is before we go on to totient functions, the Euler phi function. So, so let's suppose that we have a multiplicative function, little f, and let's say that big F is defined from little f by summing up over all the divisors of n of little f of the divisor. So the Möbius inversion formula is that we can recover little f from big F and the Möbius function by taking the sum over all divisors of the number and taking the products of mu of the divisor and f of the complementary divisor. So another way we could write this, it's the sum over all factorizations of n into positive naturals of mu of the first factor, f of the second factor. And so this is a convolution formula, and there's a whole bunch of theory involved in convolutions, which we can't really get into, but it's really a cool thing. Okay, so that's Möbius inversion. We're going to prove it, but first we need to have some properties of the Möbius function. So, so here's a lemma. For every positive natural number, if you sum up over all the divisors of that number of the Möbius function of the divisor, then you either get 1 or 0, depending on whether or not n is 1. So if you're familiar with Kronecker deltas, this is giving you the Kronecker delta centered at 1. Okay, so first, for this proof, we want that that mu is multiplicative, and I'm going to leave that as an exercise. It's a basic application of its definition. And so, by our previous work, we see that this capital M function, which I'm defining to be the sum over all divisors of the Möbius function evaluated at the divisor, is a multiplicative function, because it's a sum over multiplicative functions over divisors. So, okay, so fact 1, let's verify that when n is 1, then this big M is 1. So big M of 1 is the sum over all divisors of 1, which of course is just 1, which is mu of 1. And 1 is the product of 0 primes, so it's minus 1 to the 0, which is 1. Okay, so that matches up. Now what about when n is greater than or equal to 2? So, the otherwise. So let's suppose that p is one of the prime divisors of n, which exists because n is 2 or bigger than or equal to 2. And let's let k be the ord of this prime in n. So by multiplicativity, we can take n and completely factor out this prime power and turn it into this product of m functions. So now let's just focus in on m of this prime power. Then, so this is m of p to the k, and so we're looking at all the divisors of p to the k, so that's 1p, p squared, and so on. But we know the Möbius function is 0 for anything which has a square that divides it. So p squared, p cubed, p to the fourth, those all evaluate to 0 through mu. So all that's left is mu of 1 and mu of p. So mu of 1, that's 1, but mu of p, that's a product of 1 prime, and p and minus 1 to the 1 is minus 1, and 1 minus 1 is 0. So this factor is 0, and so we're multiplying by 0, so it's 0. So that shows that. So with that in hand, let's show that Möbius inversion actually works, and it's fairly straightforward summations, but it's a skill in its own, and we haven't talked too much about sums in the course so far. So let's see how this goes. So let's say that n is a positive natural number. We're going to show the formula actually holds by starting from the right-hand side of it. So this is the sum over all divisors of n, of mu of the divisor times f of the complementary divisor. And big F is defined by a sum itself, so let's just substitute that in. And it's being evaluated at n over d. So it's the sum over all c that divides n over d of f of c. Then we can distribute mu of d into the sum. And then if we look at this, we can see that, okay, so this is the sum over all d that divides n, and then c that divides n over d. So it's one thing that we can see from this is that for each c that divides n, we could instead consider all d that divides n over c. Or another way to say it is that c times d divides n, and we're actually summing up over all of these pairs. So it doesn't matter in which order we represent it. This is one of those old like double integral needing to swap, and you have to figure out what the bounds are. So we figured out the new bounds from swapping the sums. So then, now that we've swapped it, we can factor out f of c from this sum on the inside, and then this sum recognize it as the sum over all divisors of the Möbius function, which we saw was 1 if the thing that we're looking at divisors of is 1 and 0 otherwise. So inside the sum, the only thing that matters is when that n over c is 1, or in other words, when c equals n, all other terms vanish. So we're just left with f of n. And so the Möbius function is designed so that, the Möbius function is the unique function with this property, and that's and you can derive that if a function has this property, it is the Möbius function. And then that's the property that makes this Möbius inversion formula work. So let's look at a couple of examples. And I've put the Möbius inversion formula up here in the corner to help remind us. So little d of n, remember, is the sum of 1 over all divisors of n. And so we can apply the function that so d is the capital letter version of the constant 1 function. So we can put the constant 1 function over here, and then the formula tells us that it's the sum over all divisors of the Möbius function of the divisor times d of the complementary divisor. So again, hopefully this isn't too ambiguous with d showing up in two different ways here. So let's look at an example. Again, 18. So let's look at the right-hand side. And so this is the sum over all divisors of the Möbius function times something. That means that we only need to consider divisors that are 1 and also, divisors that are products of distinct primes. So that's 1, 2, 3, and 2 times 3. All others are 0, so we don't need to include them in this sum. And so we're summing up over 18 over 1, 18 over 2, and so on. And also, the way the signs work is when there's 1 prime in the divisor, then it's a minus sign, and when there's 2, it's a plus sign, 3, it's a minus sign, and so on. So there's this inclusion-exclusion principle going on. So this is d of 18 minus d of 9 minus d of 6 plus d of 2, which we can calculate what all those are, and indeed we get 1, as expected. So that's great. The theory actually, I guess, it stands up to an example. Or another example, remember that the sigma function, so sigma of n, is the sum over all d divides n of d. So sigma is the capital letter version, using this convention, of the f of n equals n. Right? So n, which is the little letter version of little sigma, is the sum over all divisors of the Möbius function of d times sigma of n over d. So that's just another example of what that theorem, I guess, gives us. Okay, so that was a bit about Möbius inversion. Let's head on over to looking at the totient function. So recall that the totient function is it's the cardinality of the set of all multiplicatively invertible numbers modulo n. So the theorem is that this is multiplicative, and this is where the Chinese remainder theorem comes in. So let's suppose that m and n are coprime positive numbers, and what we're trying to show is, of course, that phi of mn is phi of m times phi of n. So one thing to note is that this function f that I'm defining here, which takes as its codomain numbers 0 through m times n minus 1 inclusive, and the codomain is pairs of numbers, each with a different range. And the way the function works is it takes this number and then reduces it mod m and reduces it mod n to make this pair. So the Chinese remainder theorem tells us that since m and n are coprime, this is a bijection. And one thing to know about also is that the GCD of k and mn being 1, so in other words, if we look inside of the codomain, which numbers are going to be ones associated with the set for the totient function? So the GCD of k and mn being 1, because m and n are coprime, is equivalent to saying that the GCD with m is 1 and the GCD with n is 1. And then using the Euclidean algorithm, we can reduce k mod m and n in each of these GCDs. Okay, so k and mn is 1, the GCD, if and only if these residues are have GCD 1. So because of this equivalence, f maps this set, so the set of all numbers in the domain whose GCD with mn is 1, bijectively onto this set of numbers that are less than m that are coprime to m, and numbers that are less than n that are coprime to n. So since f is mapping this set bijectively onto this Cartesian product of sets, what that means is that if we take cardinalities of both of these sets, we get equal numbers, and the cardinality of the first set is phi of mn, and the cardinality of the second set is the product of the cardinalities, which is phi of m times phi of n. So that's one proof of this, and we might see another proof of it probably next week. Okay, so now that we have its multiplicative, it would be nice to know what its value is on prime powers, because then that helps us compute it for all numbers if we have a prime power factorization. So let's say that we have a prime number and an exponent m. Then the conclusion is that phi of p to the m is phi to the p times 1 minus 1 over p. And this is just one way to write it. And it's convenient having this p to the m on the outside for a reason that we'll see on the next slide. So phi of p to the m is, by definition, the cardinality of all k less than or equal to p to the m, such that the GCD of k and p to the m is 1. And that is, so the GCD of k and p to the m, basically if that were not 1, then that would mean that p is a divisor of k. And also if it is 1, then p is not a divisor of k. So we can just replace this with p is not a divisor of k. And then, so now what we can do, and this is slightly, that should be a less than here. So what we can do is take the number of numbers less than p to the m, which is p to the m, and then subtract off the number of numbers which have p as a divisor. And so that's every pth number starting from 0. And so that there are p to the m minus 1 of those, because p to the m is not part of the set. Right, so then we can factor the p to the m out, and then we get the formula. So putting all that together, if we have a prime power factorization, then to calculate the totient function of n, we can take n times all of these 1 minus 1 over a prime factor. So why is that? So phi of n, because it's multiplicative, is the product of phi of all the prime powers. And then, by the previous slide, each of these phi's is that prime power times 1 minus 1 over the prime. And then we can take all the prime powers and bring them to the front of this product. And of course, this is the prime power factorization of n. So we can replace it with n and get the formula. So here's an example of that computation. Phi of 18 is phi of 2 times 3 squared. So we have our prime power factorization. So it's 18 times 1 minus 1 over 2 times 1 minus 1 over 3. And so that's 6, just like before. Yeah, so that's phi. Now, there's an interesting thing about phi, which is that it has this divisor sum formula. So if you have a positive natural number and you sum over all the divisors of it, of phi, then you get n. So one thing is that, so since this function, the sum over all the divisors function, is a function of n, let's call it capital phi, that's multiplicative, as we've seen before, because it's a sum over multiplicative functions. So because of multiplicativity, all we have to do is show that for prime powers, this thing is true. So let's do that. So let's say p is prime and m is an exponent. Then capital phi of p to the m is the sum over all divisors of p to the m, phi of d. But p is prime, so we just have to sum over all exponents of p to get the sum. Now, one thing is there's this distinction between phi of 1 and also for higher powers. So phi of 1 is 1 because sort of accidentally, the GCD of 0 and 1 is 1, where usually 0 is not coprime to a number, but 1 is the unique number where 0 is coprime to it. So phi of 1 is 1, so let's pop that off the front of the sum. Also, as we saw, so p to the k for 1 through m, we can just apply the formula that we calculated before. And then, then we can use the fact that we can pull the 1 minus 1 over p out of the sum, like so, by distributivity. And then this is a geometric series. So I guess another thing is we can pull 1p out because it starts at 1, and then use the geometric series formula. So we get this expression, which we can reduce to p to the m, and then there we go. That's the that shows what we wanted to show, and by multiplicativity, we get this equality. And I thought I'd show you one thing that this lets us say. So since we know that the sum over these phi functions over divisors is n, then by Möbius inversion, we can recover phi by, because this n is like the big phi function now. So we can recover phi from this function. So phi of n equals n using the big letter notation. And so using the Möbius inversion formula, it's the sum over all divisors of the Möbius function of the divisor times the complementary divisor itself. So we can pull the n out and then get this formula here. So for example, using 18 again, phi of 18 then is 8 times, again, this is the Möbius function, so we only need to look at square-free divisors, which are 1, 2, 3, and 6. And then 6 is 2 primes, 3 is 1 prime, 2 is 1 prime, and 1 is 0 prime. So we get this 1 minus minus, or plus minus minus plus pattern here. And we're summing up over 1 over each of those divisors, which we can check as 6. So that's good. So that gives us a completely different formula from the one in this corollary to calculate the phi function. Okay, so in summary, we looked at the number of divisors function, the sum of divisors function, the number of numbers with multiplicative inverses mod a number function, and the Möbius function, where that's the totient function there. And we saw that, and we also saw what multiplicative functions were and some of their properties. And they can, one thing is that you can reduce their calculation to calculating values for different prime powers. And we saw that these are all multiplicative functions. And we also saw some examples of Möbius inversion for multiplicative functions. Okay, well, that is all I have to say today. And I will see you next week, but it will not be in this format because we are now meeting in person, but they'll still be recorded. Anyway, we'll see how that goes, and I'll see you next time.